Hello. All right. Hi, I'm Derick. Welcome here this afternoon. I am PHP 7.4's release manager as one of the things, which means it's my job to package PHP 7.4. Hopefully that comes out on November 28th. I've written an extension called xdebug. You might have heard of it. If not, type it into Google. You'll find out soon enough. I host a podcast where I talk about development of the PHP language. So discussing which new features are going to be put in or related things on phpinternals.news. If you're interested in listening to podcasts, there's 35 episodes to go through. But without anything else, I'd like to jump straight in. This is going to be quite dense material. I hope to not explode our collective brain too much, but we'll see how that goes. Okay, so what I'm going to talk about is not moon stages, but I'm going to talk about the different stages that PHP has for going from a file on disk, hopefully with PHP code in it, to executing it through the engine. And we'll have a look a little bit at what happens in all these different stages and how this is all linked together in PHP source code. So there are four main stages here. First of all is to parse the script. This is a step where we convert your code that you've written into tokens. We'll have a look what these are soon enough. Then from this stream of tokens that comes out, we're going to turn that into an abstract syntax tree. That is a very difficult word to pronounce, so I'll call that AST from now on. This AST is then turned by the PHP engine into executable code. We call these opcodes. Nikita already mentioned them earlier yesterday, but we'll actually have a deep dive into what these actually are and how they look like, and with some interesting things around them. And then the PHP engine then knows how to execute this bytecode. If you have things like opcache loaded, then the first three stages are only going to be done once per PHP process, and the rest is just going to be read out of the shared memory and executed directly. So most of these stages are done only once. All right, said so. So the first step is the parsing. And the parsing stage starts with an enormously big file. It is a big file that defines all the different possible states that you have while parsing a script. And what I mean by a state here is that, well, if you start with a file, you don't start being in PHP until you see the PHP opening tag. Before that, it's basically HTML or just text that's being sent to the browser. So a state is initial. We don't know whether we're in PHP yet. And then we have ST in scripting, which is a state that PHP switches to when it detects this PHP open tag, which you'll see in the example here. So once you have the opening tag with or without a new line, it's sort of a regular expression, sort of not 100% the same, but it looks similar enough. It will then switch to a different state. Now, other states that are there are, if you're in double quotes, there's different parser rules because the $sign does something slightly different. There's st_now_doc if you use like the arrow with end mark and stuff like that. So these are the different states. And the tokenizer is the big state machine that switches all between all of these things and tries to pick out all the different words that make up a script. But while doing so, it doesn't give any meaning to it. Luckily, we can have a look at this because PHP comes with a tokenizer extension. So let's have a look at a script. This is an example of something I've come up with. It has no specific meaning. It's just a tiny script, just to see what it does here. So we have this script. Showing the tokens didn't fit on one slide, so I just cut it in half to make it a bit easier. So what comes out of the tokenizer extension is the following. It starts with topen_tag, and if the token is something else besides a single character, each token will also have a string associated with it. So if you have topen_tag, you have the PHP open tag, but if you would use a short open tag, you'd still see T open tag, but then the string in there would be just a short open tag without the PHP in it, for example. So these tokens are now something that are being generated. You see that there's T whitespace for the whitespace keyword. There's TWS, that's just whitespace. That still exists in the tokenizer. It actually will have the length and what is actually in there, but I removed that from the slide here. Then you have T-string, and T-string is DRAM.io. DRAM.io is, in this case, my namespace name. But in the tokens, you don't see that DRAM.io is actually giving the meaning of a namespace name. It just says there's a namespace keyword followed by a string that says DRAM.io. So that's what the tokenizer ends up doing. There's tokenizers for tpublic, tclass. Basically, any keyword you see in the PHP language will have a token associated with it. I'm sure there's an exception here and there, but let's not dwell on those. So that's what the tokenizer does. At the end of the stage, there's a stream of tokens. But of course, these tokens don't particularly mean anything. So the next step in here, I know there's a lot of code on this slide, don't worry too much about it. These tokens need to be matched against grammar rules. It's the same as you have in a normal language, right? You have words, but those words don't really mean anything until you apply the grammar. And it is exactly what PHP does as well. It tries to match the tokens to specific rules, and the rules are the ones here in lowercase letters with a colon behind it. So the first one, when PHP just starts, or when you are scanning PHP code, it starts with top statement. And you know that at the top of your PHP script, what can you have? Well, you can have a namespace declaration, you can have a class declaration, a function declaration, or just statements, just some random PHP code. To make this a bit smaller, I removed some of the possibilities here, so there's not a full rule here. But you can sort of see how these things go. So forget about namespaces for a moment. Think that the first thing that we have in a PHP file is our class declaration statement. Now, what consists out of a class declaration? Well, it is class modifiers, they're the abstract and final. You have the token T class, that's the class keyword. Then it does something with line endings, so it remembers on which line these things are being created, which is the thing in the curly brackets that says send line no. T class is followed by T string, which is going to be a class name, which is then followed by potentially whether it extends for something or whether it implements some interfaces, whether there's a comment, a doc comment for your class, and so on and so on. So each of those rules is trying to be matched against the tokens that come through, and if it matches, the actions in between the curly braces are being run. And in most cases, they will have a function that says send AST create declaration, or send alt class modifier. All these things, all these functions written in C, build this tree that represents the contents of your script. Okay. So the scanner gives meaning to the tokens, and it creates this AST through rules. This file, although not written in C, well, it's sort of C, gets converted by a tool to a big C file. And that C file is a very big state machine. It has thousands and thousands of cases. Do not ever try to edit that file to add things to the PHP language. It is a lot harder. I wouldn't know how to do it, and you'll probably mess up anyway. People have tried and failed. Don't do that. Edit the file that actually has the rules. That's much easier. All right, so after this point, you then get this abstract syntax tree, or AST for short. The AST basically describes the structure of your script. Each node in it, each node in the tree, is a language construct. If class declaration, function declaration. Nested structures are represented by branches of this tree, but not all the information of your original PHP script is being kept. Things like comments in your code, they're being thrown out, unless they are doc blocks that you can do in front of classes and function names. There is also an extension written by Nikita called the PHP AST extension that can visualize those trees. And theoretically, it would be possible when you look at the tree to find out whether there are branches that can never be reached. But PHP and opcache currently don't do that. Maybe in PHP 8. Okay, the output of this AST parse code function, which basically gives you the big tree, is a very complicated structure that, well, you can see my scroll bar on the right-hand side. It gets very big. So luckily there's a way of formatting that, and that makes it a little bit easier to read. Now, as we have seen already, a script consists of top statement, and the top statement is represented by the first line in the tree, which is AST statement list. You can have constant definitions, which I stripped out here, and then you have a class definition. And in this class definition, it has multiple arguments, right? It has flags, whether it's an abstract or final. In this case, it's 0, so nothing there. It has a name, it's called whiskey. It doesn't extend any other class. It doesn't implement any interface, because those are both nulls. But a class, of course, has statements in it, right? I mean, an empty class is also possible with kind of pointers. So in this class, there are a few definitions. The first one is a AST prop decl, stands for property declaration. It has a modifier private, which means we're defining a private property. And then the name of it is also name. So this line under the 0 colon basically says there's a property, a private property called name, and the default value of it is null, meaning it's not, doesn't have a default value. Then the second statement in there is a method declaration. This is a public method. It is the construct method, that's the name of it, so it's a constructor. And then, unlike a declaration, it has a list of parameters or arguments, which are the arguments that you would give to the constructor. So in this case, we're adding an argument called name, and again, it doesn't have a default value. Again, there's lots and lots more statements, but for understanding how this looks like, this probably should suffice. So after we have this tree, we're going to do more things with it. To link this better, a bit better, just by highlighting the colors in here, to what it represents in the original method name. So we have the name construct, which is the thing in green. We have the assignment, which is the purple equal sign, which I think is a bit hard to see. On the left-hand side, we have this name. And this is not a simple variable, right? It's an expression. So the expression here is a property expression, which you can see in the light blue, where the expression on the left-hand side is the expression that is the this variable, and on the right-hand side you have the property name, which is name. Then the other argument to the assigned statement is the right-hand side of the assigned statement, which in this case is a normal variable called name. So this is how this gets built up. We have this big structure that would be great for static analyzers to have a look at, to find out whether you do things that your coding standards don't allow, or it enforces method names and, well, can do everything you can do because you have the script in a very structured way. All right. Now we need to get from this AST to bytecode. For this, it's a fairly simple algorithm that does that, because it starts with the top node and then goes to every node underneath there and then converts those bits to bytecode. Now, what is bytecode? In PHP, we also call them opcodes or opcodes. Where that name comes from, I don't know. Each function, method, or main body of a script is represented by its own operator, which means that the constructor has its own, the drink whiskey method has its own, the full body of the script has one, and so on and so on. Each of these operators contains a list of opcodes, and these are instructions for the Zend engine. We're going to have a look at those in a moment, but you should think of them as assembly instructions for the Zend engine, the engine that runs PHP. So the engine executes each of these opcodes in turn, and depending on what it does, it runs some code. There's an extension for this. Actually, there's multiple extensions for this. The one I tend to use is called the VLD extension, because it's the one I wrote a long, long time ago. So let's use the VLD extension to see what opcodes are being generated. So again, we have this AST on the top, right, where we have the constructor, and the only thing it does is it assigns the value of the name argument to the property that is this name. Now, in the bottom half here, we have a list of opcodes that are being generated here. And it is important to know that each opcode can have one return value and it can have two operands. The first one in this line, on line 8, is xNop. Nop stands for no operation. Basically says do nothing, go to the next one. opcache will remove that line because it doesn't do anything, so it can optimize it out. The recv opcode stands for receive, which means bring in an argument that is being passed into the function into the variable represented by !0. An optimization in PHP 5.3 looks at all the variable names that you have in a specific method, collects them and adds them to a list and assigns an integer number to them. In this case, we only have one of them, which is name. And this is just a shortcut instead of having to look up the name every single time it sees the name. So we call those compiled variables. After that, you get X statement, XSTMT. This is a point where debuggers like Xdebug can pause the execution of your method or function. You can have that together with opcache. It's kind of pointless, but you can have that. But the more interesting comes to the next bit, which is the assign obj object opcode. What this does is it assigns a property to something else that follows. So this is doing the assignment. So I have said that each opcode can have one return value and two operands. So in this case, there is only one operand, which is called name, which is a bit weird because it still uses the this as well, right? So it is assigning the property name of this. But because it's empty, it is implied internally that this means this. That's another optimization in there. Then the line below it that says OP data. And OP data is necessary to be able to add extra operands to an opcode because it cannot have more than two. But for assigning a property, you need the name of the variable, the name of the property, and the value that you're assigning. And because that is 3, you need to have additional OP data opcoder. So this is a very simple function. It doesn't do a lot. However, this gets more complicated depending on what kind of code you run. So let's have a look at jumps. Not this one. This is a crazy one. I have been at a point where this photo was taken, but nobody was jumping from the one side to the other side. They were climbing up though, which is still pretty crazy. All right, so let's have a look at an if statement. An if statement is pretty simple. You have an expression on your left-hand side of the equal sign and an expression on your right-hand side. So in this case, we're comparing A to be 42. And if A is equals 42, then we're echoing to life, the universe, and everything. Had to come up with something here, right? If we look at the statements that are the AST that is being created, it only has one entry in it, which is the if element. And the if element, as you all know, it has a condition, the thing that is being compared to a list of statements that is being executed if the if statement matches. So in this case, the condition is a binary operation where we compare the left side, which is AST var, stands for variable, so the variable A in this case, with the right-hand side, which is the constant value 42. And if it matches, we're doing AST echo, where we echo out the string. This gets converted into 6 opcodes. The first one is X statement, where Xdebug can pause. The first real opcode is equal. So what does this do? Well, it takes 2 operands. It takes a variable represented by !0, the variable A, comparing that with 42. Is equal, as you would expect, gives a return that determines whether the variable and the value are the same. And if so, it returns that in the temporary location tilde1. The tilde represents a temporary variable used in the engine. But it doesn't react on this. It just does the comparison. The next instruction is the jump instruction, which is exactly the same as GOTO is. This one is jump Z or jump Z. It is an opcode that will execute the jump if the first operand is false. So in this case, what it says, if the previous condition didn't match, then we're going to jump to line or opcode number 5. And opcode number 5 is the one just below the echo. So the reason why it does the jump up front, because if you didn't do the jump up front, then you need an additional jump to be able to jump out of it. So there is some logic in there that sometimes put these jumps in different places. What is a bit curious here, though, is that where does the return 1 come from? Every opcode will have a return at the end. If it is a file, the return value of a file is 1 by default. If it's a function, it will be null. PHP implicitly adds a return statement to any opcode. Now, later version of PHP will strip this out and opcache gets rid of them, but it is always generated, which is kind of a weird thing. Which means that you can do, if you do an include of a file, you can actually return a value from that. And some caching packages actually do that. All right, this gets more complicated if you get more complicated structure. So let's have a look at the if with the else. So in this case, we're comparing a to the value of pi, or a truncated value of the version of pi. If it matches, we return circles, otherwise we return squares. The AST on the right-hand side, again, is one if statement. And the first one in there is AST if element, where we compare the A with the value which is sort of pi. And the statements is one that matches is echo circles, right? Which is the first statement under the first element in AST if element. The second one is our else part of our if statement. But this is also created as a AST if element, except that it has no condition, which means no checks are being created before this gets being executed. If there would have been an if-else statement, it would also have been an if element, but it would have another condition, because you can then have them in order. Now from this, 9 opcodes are being generated. So again, you have this is equal in opcode 1, where it compares the variable a with the value that represents pi. Again, if it doesn't match, we're going to jump to op line number 6. And if you look at that in 6, that's the X statement, actually we can pause, and then it echoes squares again. And then it returns, like it did previously. Now, if it wouldn't have, if the equality did match, then the jump instruction on the second opcode wouldn't have executed. It would have executed circles, and then you get a jump instruction, not a jump Z, a jump instruction without any qualification, which means it always jumps to the line, to the op line that is being specified, in which case is 8, which then also jumps over the echo squares, because you don't want to execute it, right? Which means that all of your if statements that you have in a script are always going to be converted into jump instructions, which is pretty much a GOTO statement that you have there. All right, we have done simple if statements. You also get loops. For example, for loops. So the first for loop, it gets a bit more complicated. Every step is going to get more complicated until we run out of time. So the first one, a for statement, has 4 elements to it. It has an initial statement. We set I to 0. It has a condition where we compare whether the value I is less than 42. We have a post-loop list of statements. In this case, our only statement is a pre-increment of I. And then we have the statements itself. So the AST represents all those 4 different bits. We get the initial statement, which is a list of statements. You can have more initial statements in your for loop by using a comma. In this case, we only have AST assign, where we assign 0 to the variable called I. Our conditions is one condition that is a binary operator where we compare I to the value of 42. Then we have the loop, which is the thing that gets called at the end of the loop, where we pre-increment the variable called I. And then we have the list of statements, which I left out because I ran out of space on the slide. And again, if you look at what is being generated, the order is kind of weird. And in order to better illustrate this, I've actually rewritten my for loop to statements with GOTO. Now, I would not recommend you do that yourself, but it illustrates how this for statement gets first converted in this single list of things before the opcodes are being generated. So you can rewrite a for loop. Again, please don't do this in production code. In a different order, right? You can first do the I equals 0, jump to the condition. In a condition, we compare I with 42. We assign it to the variable called underscore, because I had to come up with something that wasn't a real name and represents a temporary variable. And if that instruction matches, which means that, if it doesn't match, that means the condition still holds, we're going to go to the list of statements by using the GOTO label stmt. Then we run echo I, increment the variable, we run the condition again. And if the condition still matches, we go back to statement. So that's what creates your loop here. This same order is represented in the opcodes. We first do the assignment, we do a jump to line 6. The PHP engine or the Zend engine doesn't actually use names for lines or oplines, it uses numbers. Computers don't care how things are called, right, as long as it's all numbers for them anyway. But it does do exactly the same thing. It jumps to op line 6, where we do the is smaller. Does it fit? If it matches. If it matches, which jump NZ stands for jump not 0, or basically jump if it is true. So if the condition matches, we're going to jump to line 3, which is what the one all the way in the bottom says. And again, at the end, we have this return 1, because this is a simple PHP script. So a loop gets unrolled into a list of opcodes. Same with do while, similar concepts, slightly different order. Most for loops can be rewritten as a do while loop anyway. We don't necessarily want to do that, but you can. There is nothing different in this output except that the order is, so I won't go over it line by line. However, one thing I do want to see that you see in the E, I, and O columns, you see arrows, and these arrows indicate, if it's under the I column, whether it's the start of a branch, and under the O, whether it's the end of a branch. And this is something that tools like VLD or Xdebug can use to find out which possible ways you have through a function. We'll get back to that in a moment. I just wanted to point out. The E, for example, stands for entry point in a function. That isn't always the first line. It can also be when you have a catch statement, because a catch can catch an exception from outside of the scope, and hence that is also an entry point. I think I have a slide for that too. Right, so for each gets a bit more complicated yet again. But it's pretty much the same thing. When you look at the opcodes that are being generated, well, first we have the assignment. The assignment of an array of constant values in the VLD that's represented by pointy brackets array to the variable A, which is the exclamation mark 0. Then we have FE reset. And FE reset R stands for each reset only in read mode. The underscore R or underscore W or underscore RW that you see in other places stands for read, write, or write. In this case, we only have a read. It has a return value, which is $4, which is another type of temporary variable. It has two operands. It has exclamation mark 0 and a jump instruction to line 11. So basically what this instruction does, it creates an internal array pointer that it can use to loop over the array or generator. It's the same initial thing. If the array doesn't exist or is empty, then it will jump immediately to opcode 11, which is FE3, where it frees this pointer to follow the array, which has been allocated in FE reset. If you allocate something, you need to free it, so that's what the FE3 is for. FE fetch R is an opcode that has a return value, which is the tilde5, a temporary variable. It has the operand $4, which is the result. It basically represents this pointer that points or scans through your list in this case. We have $1, which is a variable name value. So that is in the for each line, it is the value part behind the arrow. And then we have another operand that jumps to line 11. What is weird about this? There are 3 operands, and every opcode can only have 2. But that's a bit of a lie, because there is an extra flag, which is extended info, where interesting things get stored. For example, if you're reading a property, whether it's a static property or not. In the case of other opcodes, like FE fetch R, this extended value can be used additionally to specify a opcode to jump to. So technically, this isn't an operand, it is some extra data that we tuck on, but it saves us from having to create an OP data structure. This extra bit can only be used to jump to a specific line. It can't be used for attaching other information that we saw with OP data in one of the former slides. All right, we then do the assignment in line 5, where we assign the result of the previous FE fetch to the variable called $2, which is key. If in our for each loop we would only have had A as value, this assignment would not have been generated, and neither would the temporary variable tilde5 being created for you. Anyway, at the end what happens is it does the echo of the text, or in this case it does 2 echoes, one for each of the values that comes out, one for key, one for value. And then it has this jump instruction that has no condition. But it jumps now to the FE fetch R. That tries to pick up the next element out of the array. If it works, we continue the loop, but if there's no more elements, it will then jump to line 11, where it then ends up cleaning up this pointer and then ends the script. So that's how for each is implemented. Now, you might know that in PHP, a GOTO statement, you can only jump out of constructs and never into constructs. This is one of the reasons, because what would happen if with a GOTO statement you do a GOTO to a location inside this for each loop? Well, it will get to the jump instruction at the end, that works, but then it would jump to FE fetch R, which requires this array pointer thingy that scans your array to be allocated. But it isn't, because that gets done in FE reset R, which means that you end up accessing information that you actually don't have, and that is never a good thing. It would probably result in a crash unless some very complicated rules are being put in place so that this doesn't happen, which would make PHP a whole lot slower. All right, so complex loops, you have a for each loop, if statements in there, this gets more and more complicated. So I will leave this as homework for you. Yeah, and you can make graphs on that. Yeah, I usually find a graph easier to show what it does, but again, I'll leave this as homework for you. All right, let's have a look at. It is of course possible that you write code that you never get executed. We call this dead code. An example here. We have an if statement where we echo 40, we do a return statement, and then we echo 2. I know, this is a very trivial example. Which means that the echo 2 can never be executed, right? Because there's always a return statement in front of that. Other places where you see this, where you throw an exception unconditionally, code below it can never get executed because the exception would always come out of the structure that it is currently in. VLD can find this out by following all the possible paths it finds. So on the graph on the right-hand side here, this is sometimes slightly generated information. So the underscore main pretty much means the start of a file in PHP. This is called main. Well, the first opcode in there, it says OP0 and 1, which is represented in the opcodes by the is smaller and the jump z. The result of the jump z can either be we jump to line 5 or we continue with the next one. So that creates a branch, right? Hence in the graph, there's 2 arrows coming out after OP1. So it's either the bit that's represented by 2 and 3, which is the echo and the return null, or on the other side, it is the implicit return, the return 1 as the end of the script. But opcode 4 doesn't fit in either of these branches, and it's also not hit anywhere else, meaning it can now be flagged as that code. VLD does this, Xdebug does this for generating code coverage reports, and opcache does this as well, because it is absolutely safe to just get rid of that echo line. Both VLD, Xdebug, and opcache are a lot better at removing code, and opcache even will remove useless statements that it can infer that are not being used at all. For example, you have a method where you assign an array to the variable a, and then you assign something to b, and then you only return b. Because the statement, the assignment of a is useless, it doesn't have any impact, opcache can just remove the whole line. Which is great, because that means that the worse your code is, the faster it runs after opcache has gone through it. I think Rasmus has a quote that says, opcache is really good at making crappy code faster. Luckily, there are tools that can help you so that you don't write it in the first place, which we do, for example, which we do with things like code coverage in PHP unit. That report will tell you where you have that code so you can enable it, and there's lots of other tools that help you do this. Okay, so let's have a recap here. What did we look at? Well, we looked at the different stages, how PHP goes from having a file to running it. So we start out with the code that gets turned into tokens by the tokenizer. It gets turned into the AST by the parser, and that gets turned into the bytecode that PHP or the Zend engine then executes. Doing instructions line by line, meaning that all looping structures are having to be turned into this single line of things to run. We've had a quick look at code analysis. How can tools find that code? I can probably do an hour presentation about that, but I'm going to get kicked off in about 6 minutes. So I don't have the time for that today. We've looked at a bunch of tools. They are all open source tools. They will come without warranty. The tokenizer is part of PHP, so that should be safe to use. PHP's AST extension by Nikita has a reasonable release cycle. The VLD tool by myself compiled a Git master branch because I don't make releases. But you can still use it, so there we go. Having said all of that, are there any questions? Somebody magically is going to print. And while the questions are coming, can I have my slides back?
Your slides back? Yeah, sorry.
Thank you.
Podeu posar les...
There's a QR code that goes to the link below it, where you will be able to find a copy. And if you have questions, feel free to email me.
Okay. So I guess this counts either as a developer or as a release manager. They're asking about what you think are the changes that happened lately to the language that allowed to get such performance improvements or speed improvements.
So at the moment, there are very few endeavors that... There's lots of work being done on the PHP engine itself to make it go faster. But there are very few things that look as PHP code to make things go faster. Nikita already touched a little bit about that yesterday, like having the type declarations for variables don't make things go faster, although it potentially could. But internally itself, PHP is being improved all the time. I haven't seen any benchmark from PHP 7.4 yet, But I'm looking forward to see those when it comes out in 2 weeks' time.
Hopefully.
Hopefully.
And someone's asking about the biggest performance bottleneck that either you introduced or someone in the PHP internet lately, if there was any.
The highest,
Performance backwards, like bottleneck or something like that.
well, the highest performance bottleneck is difficult to say because Dmitry managed to squeeze out almost everything that is possible to squeeze out of the PHP engine. And that's where he is mostly looking at having this JIT engine that would add an extra step to the stages that I've just shown you to go from bytecode directly to things you can run on the CPU. This is not, sorry, I wasn't.
Sorry.
This is not a simple task, and it is to be seen whether this actually gives us a faster running PHP, because it's going to depend on so many factors.
People are asking if the abstract syntax tree builder and translator for C code have any test coverage and what it is.
There's test coverage for everything. So yeah, generating the AST, there is definitely that. I'm not quite sure what kind of test coverage Nikita's AST extension has. I'm going to ask him later. Yeah,
and then people are asking if potentially it would be advantageous to potentially explore having PHP running in other virtual machines like JVM, CLR, and if that potentially might introduce extra performance or that would be an insane work.
It could introduce extra performance, but I can't see this ever happening. Because it basically means rewriting the whole stack to target a different virtual machine. If you want to use a different virtual machine, use the language that they already support, I would say. I think it's pointless for PHP to do that.